Hi, my name is Noam Mazor, and this talk is about incompressibility and next block pseudoentropy. This is a joint work with Iftach, Haitner, and Silbak. Let me start with talking about pseudorandomness, which is a computational analog of randomness, and a basic concept both in cryptography and complexity. In the context of cryptography, we define pseudorandomness as follows. We say that a distribution x over n bits is pseudorandom if we cannot distinguish between x to the uniform distribution over n bits, or if x is computationally close to the uniform distribution. We define computationally closeness as follows. We said that x is computationally close to y if for every efficient algorithm A, the probability that A output 1 on a sample from x is almost the same as the probability of A to output 1 on a sample from y. And formally, in order to talk about efficient algorithms or polytimes algorithms, we need some parameter that goes to infinity, or to talk about ensembles of distributions. But for simplicity in this talk, I'm going to ignore it and talk about specific distribution. The reason that pseudorandomness is so useful is that we can use it in order to construct pseudorandom generators, which is a primitive in cryptography that can be used in order to construct, for example, encryption schemes. Pseudorandom generators is just an efficient computable function g from L bits to n bits, such that the output of g on the uniform distribution over L bits is pseudorandom. And in order to make this definition useful, we require that L is much shorter than n. So a question we can ask is how to construct pseudorandom generators, or in other words, how to construct pseudorandom distributions. To understand it, we need to talk about randomness and how to construct randomness. And for this, we need to understand entropy. Entropy is a refinement of randomness, or actually a measure of randomness. The entropy of a distribution x is defined to be the expectation over the distribution x of the log 1 over probability to get a specific sample from the distribution. We think about the log 1 over probability as the amount of surprise we have in this specific sample, or the amount of information we have in this sample. And by taking expectation, we get the expected amount of surprise in the distribution x, or the expected amount of information in x. Entropy has a few nice properties. One of them is that the entropy of x is the expected number of random bits that we can extract from the distribution x. So for example, if x is the uniform distribution over n bits, we can extract from it n bits of randomness. And indeed, the entropy of the uniform distribution is n. And for other example, if x is with probability half bottom and with probability half the uniform distribution over n bits, then the entropy of x is n over 2 plus 1. And indeed, we can extract from x n over 2 plus 1 bits on average, because we can extract 1 bit from the event that we got bottom or not. And with probability half, we get additional n bits. Another property that entropy has is that the entropy of x is the minimal description length of x, or the minimal compression length of the distribution x. One property that makes entropy very useful is the fact that we can convert entropy to randomness. So if we have a distribution y with entropy at least k, then we can use an efficient procedure that we call the extractor, that takes a number of samples from y, and for each sample it outputs k bits, such that if we get the extractor samples that run from the distribution y independently, then the output of the extractor distributed uniformly, or close to uniformly. So the extractor extracts from each sample of y roughly k bits of randomness. And in the computational settings, we know we can convert pseudorandomness, we can convert pseudoentropy into pseudorandomness. Pseudoentropy is a notion defined by Astabin, Pagliazzo, Levin, and Luby, and we said that the distribution x has pseudoentropy k if there exists a distribution y with real entropy at least k such that x is computationally close to 1. In other words, x has pseudoentropy k if it is indistinguishable from some distribution that really has entropy at least k. And Astad in Pagliazzo, Levin, and Luby showed that if we apply extractor on x with pseudoentropy, we get pseudorandomness. This is because if we apply the extractor on y, we get something which is indeed close to randomness, and we cannot distinguish between x and y. So we cannot distinguish between the output of the extractor on y and the output of the extractor on x. So the output of the extractor on x is pseudorandom. And this is useful in order to construct pseudorandomness. And indeed, Astad in Pagliazzo, Levin, and Luby showed how to construct pseudorandomness using this notion. And pseudoentropy is a computational analog of entropy in the same way that pseudorandomness is a computational analog of randomness. And the point here is that by defining these computational analogs of entropy and randomness, we are able to apply information theoretic tools in the computational settings. So computational analogs of entropy are very useful in order to construct cryptographic primitives, but we can try to come up with alternative computational analogs of entropy. And in fact, alternative computational analogs of entropy used to construct more efficient pseudorandom generators. And the general approach to come up with computational analog of entropy is to first identify some property the distribution with high entropy have, and then to come up with a computational analog of this property. For example, Yao showed in 82, Yao defined the next bit unpredictability property. He said that a distribution x over n bits is next bit unpredictable if for every efficient algorithm or predictor that treats x bit by bit in an only fashion, the predictor cannot predict the next bit of x given the prefix. So his advantage in predicting the ith bit of x given the I minus 1 length prefix is at most half. And without the restriction on the efficiency of the predictor, this is just an information theoretic property that random distribution have. But by limiting the predictor to be efficient, we get a computational analog of this property. And in fact, Yao showed that next bit unpredictability is equivalent to pseudorandomness. Okay? So, till now we saw a number of computational analogs of entropy. We defined pseudoentropy. We talked about next bit unpredictability. And additional computational analog we knew is next bit pseudoentropy, defined by Haitner, Reingold, and Vadam. Next bit pseudoentropy is a quantitative refinement of unpredictability. Instead of asking that the predictor cannot predict entirely the next bit of x, we only ask that the next bit is somewhat auto-predicted, and we quantify this hardness exactly. And next bit pseudoentropy can be converted to pseudorandomness using repetition and extraction techniques, and thus it is useful in order to construct pseudorandomness or pseudorandom generators. And in fact, the best construction of PRGs we know today use this notion. But at least both next bit unpredictability and next bit pseudoentropy capture the unpredictability property of a distribution with high entropy, and we can try to come up with notions that capture other properties that entropy have. In other contexts in cryptography, like cryptographic hash functions and commitments, there are other notions of entropy, like inaccessible entropy, but we are not going to talk about them today. Today I want to talk instead on compressibility. So a compression scheme for a distribution X is just a pair of algorithms, encoder and decoder, such that for every X in the support of the distribution, if we encode X and then decode, we get back the same sample X. And our goal is to minimize the expected encoding length of X. Now, just notice that the encoding length of every sample from X can be different. This is not a fixed length encoding scheme. And Shannon showed that for at least for useful compression schemes like prefix-free schemes, it holds that the best compression scheme from X, the expected encoding length is at least the entropy of X. And also we know that for the best compression scheme, the expected encoding length is at most the entropy of X plus 1. So there is a tight connection between compressibility and the entropy. And then Yao came up with a very natural computational analog of entropy, which he called the effective entropy of X, which is just the minimal expected encoding length of X when we only consider efficient encoding and decoding procedure. And this definition is also called incompressibility or Yao's pseudoentropy, and we are going to refer it as incompressibility. So let me define it more formally. We say that a distribution X is k-incompressible if for every poly-size compression scheme encoder and decoder, the expected encoding length of X is at least k. And this is a non-uniform definition. You can come up with a uniformly variant of this definition, but this is the way Yao defined it. And the connection or relations between this definition and other computational analog of entropy is not well understood. There is a stronger worst-case notion of incompressibility that Barak, Chartier, and Wigderson showed that if we have a distribution with this stronger notion, then we can extract from it k minus omega of log k pseudorandomness. And this was used in order to construct PRGs from hardness in the complexity context. But again, this is only from the stronger notion. So just as a quick recap, we've seen three computational analogs of entropy. We talked about pseudoentropy. We said that the distribution X has pseudoentropy K if it's indistinguishable from some distribution Y that really has entropy at least K. We talked about next bit pseudoentropy without a definition. We said that this is a refinement of next bit unpredictability. And we defined incompressibility. We said that the distribution X is k-incompressible if we cannot compress it efficiently to less than k bits. And now the main question of this work is what is the relation between incompressibility to other computational analogs of entropy? And we also ask if non-trivial incompressibility imply cryptography. By non-trivial, I mean a distribution that cannot be compressed efficiently to its entropy, or in other words, a distribution that has incompressibility strictly larger than its real entropy. And when we ask if non-trivial incompressibility implies cryptography, we ask if we can use such a distribution with non-trivial incompressibility in order to construct, for example, pseudorandom generators or encryption schemes. So let's see our results. But first, let me define formally next bit pseudoentropy. So we said that the distribution X has next bit pseudoentropy K if there exists other distribution Y jointly distributed with X such that for every I, the first I bit of X are indistinguishable from the I minus 1 first bits of X and the ith bit of Y, and the sum of entropies of yi given the ith minus 1 prefix of X is at least k. Now, if we require that the entropy of yi given the prefix of X is 1 for every I, then this definition was the same as the next bit unpredictability notion. But when we only ask that the sum of the entropies is at least k, we get that the next bit of X is just somewhat out to be predicted given the prefix. Okay. So our main theorem is that incompressibility implies next bit pseudoentropy. So we showed that distribution X, which is K incompressible, is a distribution with at least K minus 2 next bit pseudoentropy. So incompressibility implies next bit pseudoentropy. And a corollary of this theorem is that if T copies of X are T times K incompressible, then X has next bit pseudoentropy at least K minus 2 over T. So if we cannot compress T copy of X efficiently to T times K bits on expectation, then X has next bit pseudoentropy roughly K. So now how the world looks like after we have this theorem. So we have pseudoentropy, incompressibility, and next bit pseudoentropy. We already knew that a distribution with K bits of pseudoentropy is a distribution with K next bit pseudoentropy. And similarly, we already knew that a distribution with K pseudoentropy is a distribution with K minus log K incompressibility. We also knew that there is a distribution with K next bit pseudoentropy that doesn't have K to the power of 0.01 pseudoentropy. So next bit pseudoentropy doesn't imply pseudoentropy. And similarly, there is an oracle with respect to, there is a distribution with K incompressibility that doesn't have K to the power of 0.01 pseudoentropy. So also incompressibility is a weaker notion than pseudoentropy, at least with respect to some oracle. In our work, we showed that a distribution which is K incompressible is a distribution with K minus 2 next bit pseudoentropy. So incompressibility implies next bit pseudoentropy up to this 2 bits gap. In the other direction, we know that next bit pseudoentropy doesn't imply incompressibility, but we showed that incompressibility actually implies stronger notion than next bit pseudoentropy. We call it strong next bit pseudoentropy, and this notion does imply incompressibility. So a distribution with K strong next bit pseudoentropy is a distribution which is K incompressible, and a distribution which is K incompressible is a distribution with K minus 2 strong next bit pseudoentropy. So these two notions are equivalent up to this 2 bits gap. Our second result is that incompressibility implies cryptography. So when we say that incompressibility implies cryptography, we actually say that incompressibility implies one-way function. One-way function is the minimal assumption in cryptography, in the sense that almost all useful primitives in cryptography imply one-way function. And using one-way function, we can construct many useful primitives, such as pseudorandom generators and encryptions. A one-way function is a function that is easy to compute, so we have an efficient algorithm that, given an input x to the function, output f of x, but it is hard to invert, so there is no efficient algorithm that, given f of x, output x. And in this work, we are focusing on summable distribution. So distribution x is summable if there is an efficient algorithm that, given the uniform distribution, given randomness, output samples from x, and the output of A is distributed according to x. So a distribution x is summable if it is an output of efficient probabilistic algorithm. And Haitner, Reingold, and Vadan showed that every summable distribution with non-trivial next bit pseudoentropy implies one-way function. So every summable distribution with next bit pseudoentropy larger than its entropy implies one-way function, and thus implies cryptography. And using our theorem, our first theorem, that a distribution with K incompressibility implies a distribution with next bit pseudoentropy at least K minus 2, we showed that if one-way function do not exist, then every summable distribution can be efficiently compressed to its entropy plus 2. In other words, if there is a distribution which is incompressible with its entropy plus 2, then one-way function exists. And this is because if one-way functions do not exist by the result of Haitner, Reingold, and Vadan, then the next bit pseudo-entropy of every distribution is equal to its entropy. And then our theorem says that a distribution X with K incompressibility is a distribution X with entropy K minus 2. So we can compress X to its entropy plus 2. To conclude, we showed in this work that incompressibility is equivalent to strong next bit pseudo-entropy. And for open questions, we want to find connection to other computational analogs of entropy. We want to understand the uniform variant of incompressibility. And we want to close this 2 bits gap between incompressibility and strong next bit pseudo-entropy.